Our next speaker is Chris Porter from Georgia Tech.
Hey, how's it going? Can you hear me okay?
Yes.
Great. All right. Yeah, I'm Chris Porter, and I'm presenting our work, compiler-assisted scheduling for multi-instance GPUs. My co-authors are Chao Chen and Santosh Pandey. So meet MIG. So NVIDIA built something again, right? This time it's called multi-instance GPU. So if you don't know, I'll tell you a little bit about what it does. It allows you to hardware partition your GPU. So what you're seeing here is a figure from their white paper on the Ampere architecture. This is one GPU, but it's been sliced. So there's 3 dark green boxes, which they call GPU instances. And these are hardware isolated instances. So this comes with security guarantees, like your global memory isn't shared, and performance guarantees. So another job can't hog your resources. And you can see that they each have their own memory and their own compute instances. And this is all in service to those purple rectangles at the top, our users, our applications. So question, how many applications do we have here? Well, the answer is, I don't know. We definitely have one over here on the right. And we have a second application here, I think. So it seems to be 2 applications, but they're sharing a container. So we're looking sharp. But what's going over here on the left? So I don't know how many single purpose applications that run 2 TensorFlow processes and 2 PyTorch processes. So either this application is pretty unique, or the person who designed this graphic was having too much fun, because all these processes are going to compete for memory. And when it comes to free memory, how low can you go on this GPU instance? So either these processes are going to play nice, and the free memory bar will be high, so to speak, or it's going to be awfully competitive, and the whole thing will fall flat on its back. So the point here is that MIG gives us hardware partitioning and isolation guarantees, but it has no guidance or support on how to schedule or pack partitions. Now let's formalize this a little. There's an issue. So MIG gives us the ability to partition the device, but within a partition, if you want to pack multiple jobs, life reverts to pre-MIG. We have no way of knowing how many jobs we can pack. We can choose to run only a single applications with a partition within one partition and suffer from underutilization, or we can pack more jobs and potentially crash from out of memory errors. And this problem clearly matters. GPUs are underutilized and expensive. So if you have an MIG enabled device, there's clearly an incentive to pack jobs that do not require isolation. Thus, on MIG enabled devices, there's still a need to improve GPU utilization for non-isolated jobs. So we propose a framework that can help with this. We built a compiler-assisted scheduling framework for multi-instance GPUs. We target single nodes with multiple MIG instances. Our goal is to share MIG instances among isolated jobs and non-isolated jobs. The non-isolated jobs are independent, uncooperative applications. And we show how our framework improves the system utilization with negligible performance interference per workload. We show throughput improves for a batch of GPU tasks by an average of about 1.5x. It's fully automated. We use the compiler to generate resource requirements at runtime, and we have a workload manager that makes scheduling decisions. So our talk has 3 main parts. I'll touch on state-of-the-art work, then we'll share details of our framework case, and then we'll close with a discussion about our results. So there's a significant amount of research that's gone into various aspects of GPU sharing, utilization, and performance. For example, there's work from 2011 that shows how larger warp sizes and a 2-level round-robin scheduler can boost GPU utilization. More recently, a lot of work is focused specifically on deep learning. A work called Gandiva leverages deep learning properties like early feedback to boost the efficiency of multi-job training. Another work called Marble chooses an optimal number of GPUs by profiling the scalability of its jobs. Now, a lot of this progress depends on hardware-software support, including NVIDIA's multiprocess service. So MPS is what actually enables simultaneous execution of multiple kernels on the devices. A crucial assumption for MPS, though, is that different processes' kernels are cooperative, like with MPI tasks or cooperative neural network training processes. So the developer is completely responsible for managing the memory and not overloading it, because MPS makes no guarantees on this. And if for whatever reason the processes are independent and do not know about each other's resource needs, out-of-memory errors are completely uncontrolled and possible. So we've introduced NVIDIA's multi-instance GPU. Again, now you're able to hardware partition your device. Now your jobs don't have to worry about performance interference from jobs in other partitions. And there's security guarantees for cloud or untrusted environments. And MPS is also integrated with MIG. It's still active within a partition. And lastly, we have to mention Slurm, because how are you going to manage a batch of jobs or incoming requests for these GPU resources? So Slurm is a traditional job queuing system. You tell Slurm what resources you need, maybe how much system memory, or whether or not you need a GPU in the first place, and how big it needs to be. And Slurm agrees to reserve those resources for the duration of your job. It already supports MIG. The MIG instances just appear as normal GPUs to the users. One of its main limitations, though, is that it cannot schedule two independent processes on the same GPU device. Also, if you're going to use a system with MIG today, this is the de facto standard workload manager. This is not a complete list, of course, of related work, but it's somewhat representative. Nevertheless, there's little to no work on safe, efficient sharing of independent, uncooperative processes for the single node multi-GPU scenario. Well, actually, that's done now. So we actually built Case originally to tackle multiple GPUs that don't have MIG support. And we're presenting that at PPOP. So if you're interested, quick plug, please come to our talk. It's the first one tomorrow. But what about the multi-instance GPU scenario? Can we extend Case to handle this new feature? So that's what we've done here. We've investigated how you can take a system like Case and apply it to GPUs with MIG support. The main contributions of our MIG work include a new workload manager, integration with two systems with MIG, and our experimental results. So relaxing the isolation property changes the way we have to do scheduling. And we also need to see how homogeneous versus heterogeneous instance sizes, or how varying ratios of isolated to non-isolated jobs affect this kind of approach. Now, this diagram is a high-level view of our framework and how it is positioned in a basic hardware-software stack. We can see applications sit at the top of the stack and GPUs lie at the bottom, the interface to the GPUs, the CUDA runtime, but somewhere in the middle, between the applications and the CUDA runtime, is our framework. It consists of an offline component, namely the compiler pass, but its lazy runtime and the scheduler interact during the application's execution to help direct them to a proper GPU. Note that our framework integrates with the CUDA runtime and depends on it for certain functionality, such as being able to place more than one application on a single GPU in the first place. Now, here's a simple motivating example of how our case framework operates for MIG. Consider two MIG instances and two applications. Also, for the sake of this example, we'll assume both applications have two kernels and that they want to schedule them simultaneously. So applications, one's kernels both fit on the instances. That is, we could assign K1 to instance 0 and K2 to instance 1. Similarly, if we take application 2 in isolation, it can assign K1 to instance 0 and K2 to instance 1. The problem, however, is that if these applications run together, there's not enough memory to support instance 1. There's not enough memory on instance 1 to support K2 from both applications. So each requires 3 GB, but each instance has only 4 GB. So if, however, application 2 assigns K2 to instance 0 and K1 to instance 1, then all 4 kernels can fit on the two instances. So how do we solve this? There's 2 parts, a compiler component and a runtime component. The compiler component is a major contribution of the PPOP work, and it's unmodified for our purposes here. I'll touch on it briefly for clarity. So in short, it uses static analysis to identify GPU tasks, which we define as any group of kernels and the related operations. If static analysis fails, it defers to a lazy runtime, computing the resource requirements on the fly. In either case, this is done via compile time instrumentation. The case compiler component instruments the application with probes that convey GPU resource requirements to the scheduler. So here's how that instrumentation would work at runtime. The compiler inserts a function called task begin that passes a GPU task's resource needs to our runtime scheduler. So following along, it sends a probe with the resource needs. The scheduler uses that to determine an available device, and then it returns a device ID for the GPU task. The process itself uses CUDA set device to select that device. That's it. And this happens through a library over shared memory. Now, how exactly did the case scheduler decide on the device for a given task? The basic idea is the following. We maintain 2 job queues, one for isolated jobs and one for non-isolated jobs. Case works at a batch level, and it depletes the isolated jobs in the batch first. The reason is that non-isolated jobs, if scheduled ahead of isolated jobs, could starve out the isolated jobs. So once non-isolated jobs have space to run, we assign them to the GPU slice that has 1, memory available for it, and 2, the least number of active warps. Note that memory is a hard requirement. An MIG instance must have memory available for the task, or we can't schedule the task on it. Compute, however, has been relaxed to a soft requirement. Once we know which MIG instances have enough memory available for a task, we just want the least loaded one. We'll show an example with Slurm and then the case scheduler to make this more concrete. So for these examples, we have one A30 GPU with 4 MIG instances. Each instance has 6 GB of memory. We'll color code our jobs too. So if the job's orange, it means it's isolated. If it's green, it's non-isolated. Gray means we don't care, which is how Slurm operates. That is, it doesn't make a distinction. So going through it, this is how Slurm operates. Here we have 16 kernels in the batch, and we're at time t0. Nothing's happened yet. At some time t1, Slurm is going to schedule kernels 0 through 3 onto each of the slices. Notice each kernel has its own slice. Slurm can't schedule anything else onto the GPU at this point, though, because by design, each job is reserving a slice for itself by way of Slurm. And at time t2, a couple of jobs have completed, and Slurm has filled the GPU with the kernels from the waiting jobs. So K4 has replaced K0, K5 has replaced K2, and Slurm would just carry on like this until it retires all jobs. So let's look at how Case handles this. Notice we have a table now. Case maintains each MIG instance's state. For each slice, it tracks the free memory, the in-use warps, and whether or not a slice is running isolated jobs. Also, our batch contains 8 isolated jobs and 8 non-isolated jobs for this example. So let's get started. Case schedules the first 4 isolated jobs. It also updates its table. So each slice is marked yes for isolated, and because isolated jobs don't share anything, we're just going to ignore free memory and in-use warps for those slices for now. This is similar to Slurm so far. And at time t2, the first isolated jobs have completed, and we have the last 4 running. Nothing too exciting yet. Now at time 3, a slice is freed up, and we can start running non-isolated jobs. At this point, the resource needs of the kernel become critical. So in the bottom left, we're showing what the next 3 kernels' resource requirements are. These resource needs were all procured via the compiler and passed to the Case scheduler at runtime. And Case is going to dequeue a kernel and place it onto a slice if one's available. And this is exactly what Case does. Here it's moved K0 and K2 out of the queue and onto the available slice. It also updates the state of free memory and in-use warps for that slice. Notice that K3 is too big to fit on the slice. It needs 4 gigabytes of memory, but only 1 gigabyte of free memory is available, so it can't be scheduled. Now, assume at some point T5, another isolated job is completed, which has freed up a slice. So Case has moved to K3 onto the new slice and updated the state. Notice that K6 is now at the front of the queue, and in fact, it looks like there's space available for it. It only needs 1 gigabyte of memory, and both non-isolated slices have this much memory available for it. At this point, Case checks the soft compute requirement. It looks at the in-use warps. So it's going to schedule K6 on the slice with the lowest compute load. We have 2 options here, 4 million warps versus 5 million warps. So the slice with 4 million warps should be the target. And that's what Case does. It schedules K6 and updates the MIG instances state. We won't complete the remaining jobs, but this illustrates how Case selects MIG instances for its jobs. All right, let's jump into the evaluation. We use 2 different systems, one with 4 NVIDIA A3s and one with an NVIDIA A100. Both are Ampere architectures. For the systems with the A30s, we also varied the number of A30s that we use. So we had a 1x, a 2x, and a 4x configuration. And all the A30s are sliced 4 times into 4 gigabytes each. And the A100 gives us a chance to evaluate with heterogeneous instance sizes. 3 were 5 gigabytes and 2 were 10 gigabytes. Our workloads are created from Rodinia jobs and neural network training jobs. So Rodinia is a traditional benchmark suite for parallel computing. We treat these as non-isolated jobs. And PyTorch is a popular framework for machine learning. We pick 4 common neural networks and train them in isolated partitions. We construct random mixes from these tasks, and we vary the number of isolated to non-isolated jobs in each batch. So to summarize the results, Case improves GPU utilization on the A30s by about 2.93x, and on average, its throughput improvements on the A30s is 1.45x. The job turnaround time, which is measured as the time between the start of the batch and the completion of a job improves by 1.39x. And the individual kernel performance degradation, which can happen when simultaneously executing kernels compete for resources on a GPU, was less than 10%. All right, this is what the A30 throughput results look like. So everything's normalized against the Slurm results. On the x-axis, we have the different batches. These are the various isolated to non-isolated ratios across the different configurations. So there's an A, B, C configuration, which indicate whether we use 1x, 2x, or 4x A30s for the experiment. The trend we sort of expect here is that as the number of non-isolated jobs increases, the throughput improvement should be higher. So I've cheaply superimposed 3 lines here to show you what I mean. Within a configuration, so for example, if you look at just the bars for configuration A, where you're using just one A30, the throughput improves as the ratio of non-isolated jobs increases. These are just randomly generated workloads, and it's just one run. So yes, there's a little bit of noise. And this is the job turnaround time for the experiments on the A30s. The trend's a little clearer here, I think. It's also promising. Like, yes, the isolated jobs get precedence, but you're also getting really good job turnaround times. So even though you have some non-isolated jobs that get placed on GPUs later than they'd usually be, you have, on the whole, faster turnaround times because you're using more of the GPU. And I'll show just the throughput graph for the A100. It's a similar trend, slightly tamer. We have more improvements as the ratio of non-isolated jobs goes up. And the last graph I'll show is what memory utilization looks like over time. So this result is drawn from the 4x A30 result with, it's a 1:4 ratio of isolated to non-isolated jobs. So the x-axis is time, the y-axis is GPU memory utilization, taken over all 4 GPUs and all 4 of their slices. So the blue line Slurm, the red line is case. Basically, case is packing better. So you can see the utilization drops off for case at the end because there are fewer opportunities for packing. But at the beginning, we can see case makes much better use of the total GPU memory available across the system. So in summary, we presented compiler-assisted scheduling for multi-instance GPUs. It's fully automated. It uniformly and transparently manages MIG resources. It combines static analysis, a lazy runtime, and a scheduler. It guarantees memory-safe execution of uncooperative processes, and it shows strong performance improvements: 1.45x boost in throughput, 2.993x in GPU memory utilization, and 1.39x in job turnaround time. Our source is available on GitHub, and please check out our PPOP paper. It gives much more detail on the compiler contributions, and it shows similarly strong improvements for systems without MIG. Thanks a lot for listening.
Thank you so much, Chris. Any question for Chris?
I do have a question. I'm wondering about your count of, you're estimating warp utilization or warps needed or something. You had numbers in the millions. Where do those numbers come from? These GPUs cannot support millions of warps.
So these would be not simultaneous, right? This is
well, I don't know. You tell me.
No, these are not simultaneous, right? It's not running 4 million, say. It could be.
So what's the point of it? I mean, you can have a long running warp or a million short running warps. They take the same amount of GPU resources. So I don't understand what's the point of counting warps.
The warps is an estimation of load. Could you repeat your question?
You could have 6,000 long running warps or 6 million very short running warps. They're going to be all, the total residency on the GPU would be the same, but the count of warps seems like a strange number. It seems like incomplete.
That's true. So we looked at just these 2 resources, right? And what we found is that, so for memory specifically, which is the most crucial one, right? We can't overblow that budget. Now, when we're estimating like compute load statically with a compiler, we're very limited, right? So we started with just warp counts here as a proxy for load, and we don't look at other things. We don't look at other memory. We just look at global memory, right? So
you look at launch configuration, basically.
Yes, exactly. And there's more information on the PPOP version.
Okay, thanks.
Are there any other questions? All right.
I have a quick question. So, MIG system is considered as totally separated, right? It's fully separated, so there's no conflict between instance to another instance. Since you're running a lot of instance, how much of conflict did you observe? Is it better than MGS? And do you have any solution to deal with these conflicts?
I'm not sure I understood this question. So you're asking about whether we encountered a lot of conflicts among MIG instances?
Yeah, let's say if you use 4G and the other one uses 3G, so is this actually slower than running than, say, 7G and another 7G in 2 piece of times?
Okay, I
do they
think
slow down? Do they slow down if they share the GPU?
yeah, okay, I see. So I think the only metric we reported in the workshop paper, and I also mentioned it here, but in very briefly, is that like one thing you can measure is like the kernel slowdown times. So like if you run two kernels at the same time on the same GPU, which previously they'd be isolated, what's the degradation? What's the slowdown compared to if you just run them standalone? So we did capture that. There's a table in the paper for this, and it's on the multi GPU case. It was even better. It was something like under 3%, 2.5%. Here, I think the max we saw was like 7.5% or so. It was under 10%. But that's just kernel degradation. Yeah.
All right, thank you very much.
Yeah, thank you.
Thank you, Chris.